Hello, everybody. Welcome to Chromium University 2020. I am Chris Bloom. I will be presenting C++ as a second language. You'll notice this is 2.0. 2 years ago, I gave this exact talk, but it was my first draft, and I got a lot of feedback, things that I can improve, and I've made some changes. Some of the changes we'll probably not worry about. For example, I covered raw pointers, which a lot of people are afraid of, and I covered templates, which are very different from other languages. But at the end of the day, uh, there really wasn't time to go into enough detail, and it was just going to be confusing. So I cut those out. If you really want to learn about them, you can go back and find the slides from 1.0 and read through all of it. You can also watch the presentation, but we didn't cover it then. As you can see here, my name is listed, Chris Bloom, and my social media is Program Max. If you have any questions, feel free to reach out to me, ask away. Speaking of questions, there's already a question. Oh, never mind, it was just deleted. Okay, let's begin. So this is the roadmap we're going to talk about. The intention here is if you are already a programmer coming from another language, what are things that are going to be strange about C++, things that aren't going to fit naturally in your mental model? And that's what I want to cover here in the roadmap. And we're going to start with free functions. Free functions doesn't mean free as in beer or anything like that, free as in speech. Free functions really just means it's not tied to a class. The function is completely independent of the class. So here, for example, I'm going to pick on Java. Java is a great language. I love it, but it's a good language to put on slides because if you're coming from Python or C# or anything like that, you can probably read the Java and understand what's going on. So throughout this presentation, I'll be picking on Java a lot. But in this first bit of code, you see class hello world app, and inside there is public static void main. The function there is the entry point to your program. And at that point, we couldn't have instantiated any classes. We couldn't have run any code yet. So it really doesn't belong to this class. In fact, you can put this function in any class you want, and it'll work the same. So that's kind of proof that this function doesn't need to be tied to a class, and it doesn't really make sense to do that. Below that, you can see class Java lang math, and inside there is public static int max. This is just a function that you give it two integers, and it returns the maximum of your two integers. That has nothing to do with a class at all. This is really, the class here is just a namespace. So in both of these examples, the reason it's like this is because Java is a purely object-oriented language. You can't have free functions. But in C++, we would write those exact same things like this. There's int main, your entry point to your program, and then there's int max that returns the maximum of two integers. You can see that there's no classes involved at all. So if you're coming from a purely object-oriented language, this will be weird to you. But I think this makes sense. Some functions don't need to belong to a class. So next up is include and linkage. So here we have, in Java, you use import. Same within Python, you use import. And you notice I kind of stacked two examples. The top one is if I'm importing a system library or something like that. And the second one is if I'm importing my own code. So at the bottom, we have C++, and it has #include instead of import. And then you'll notice there's an angle bracket version of include, and then there's a quote version of include. The reason that there's a difference here is if I try to include a file, it will have a list of paths to search. So it might say, first start at this directory. Is the file in that directory? No? Okay, now go to the next directory, so on and so forth. And it goes all the way down the list of directories looking for this file. But there's two separate lists. There's a list specifically for system libraries. I should be able to find these includes in a library that I've, like a standard library or something like that. But then if I use quotes, it goes to a second list that's specifically for my code. If this is within my project, then use my local folders. Don't try to find a system folder or anything like that. So in C++, there's what's called translation units. And every code file is its own translation unit, and they don't know about each other. So in this example, I have at the top a.cpp, and then at the bottom, I have b.cpp. Those files are both sent to an independent compiler. They're compiled separately, they know nothing about each other, and each one produces an object file. Those object files are then gathered together and sent to the linker, and the linker outputs a program. So what this really means is that there's a compile phase and a link phase. Now this isn't 100% true. Everything on these slides is going to be about 99% true. In this case, the reason it's not true is there is link time code generation and link time optimizations and all that. So it will actually do some amount of compiling at the link phase. But that's a really specialized step. It's not really standard. So you don't need to know about it. So I'm going to skip those, the 1%, the exception to the rule. You don't need to worry about it if you're coming from another language. For now, we can just envision that there's a compile phase and a link phase. So because a.cpp doesn't know anything about b.cpp, it's possible that I've written some functions in a.cpp that I'm really intending to only use here in a.cpp. I don't want it to be, when it gets to the link phase, I don't want other translation units to consider it. So you can deliberately hide functions from getting to the link phase. And there's two ways to do that. The top way is to wrap it in an anonymous namespace. So you can see namespace and then the curly bracket. Normally it would be namespace and then the name. Because we left out the name, this is an anonymous namespace, and that means this function is only visible within this translation unit. It won't get outside the link phase. This is kind of the currently accepted and loved way to do it, but in old style C++, you could have the second example, which is just to mark the function as static. They both do the same thing, by the way. So then the opposite side of that coin, what if a.cpp has functions that b.cpp wants to call? Somehow I need to expose those functions across translation units. So that's where header files comes in. In this example, if I have compute harmony.cpp, and that might have this function void harmony, I will pair the .cpp file with a .h file, the h being header. In the header, I'm going to forward declare this compute harmony function. The goal here is not to actually define the function, but just to say, I promise there will be a function, it'll look like this. This is the signature. So to give a more concrete example, at the top we have compute harmony.h, and it has void compute harmony, and then that semicolon. All that's doing is saying, I promise there will be a function that matches this signature. It's just a forward declaration. Then in compute harmony.cpp, the first thing we do is include the .h file, and that helps us pair up the forward declaration with the actual function body. Then after that, we have the actual function. There's void compute harmony, and this time it has an actual implementation. And then at the bottom, we have other.cpp. This is where we want to call the compute harmony function. So the first thing we do is include compute harmony.h, the header. That will make sure that when we call this function, we have the right signature and we understand what the function should look like. And then we just call it like normal. It's no big deal. The way this will work behind the scenes is the translation unit will compile it saying, I know I'm going to be calling this function. I know I'm going to be putting these parameters on the stack. However, I don't know the address of the function that I'm going to be calling. So it leaves a little mark and says, hey, linker, when we get to the link phase, fill in this mark. Give me the actual address of the function. Okay, so now to update our diagram, here we have a.cpp and it's paired with a.h, and then b.cpp includes a.h. So next up, I mentioned that there's the quote version of an include, and then there's the angle bracket of include. I want to describe to you what this does. All it does is really, really simple. It opens that file, copies the whole file content, and then replaces the include line with the file contents. Simple as that. It's just a copy and paste. But this will actually lead to a few problems. Here, in this example, we have musictype.h, and it defines a class music type. Now, previously I said we have a for declaration of a function. It was just a declaration. It wasn't the actual definition of a function. But in classes, this is a little different. Maybe I'm going to derive from a class, or I need to know the size of a class. In that case, I need to know the actual definition of the class, not just a for declaration, hey, I promise there will be a class called music type. So it's common to put the class body inside the header file. So here in this example, we have class music type, and it has a pure virtual function play music. Below that, we have jazz.h, and it includes musictype.h. And we have class jazz, which derives from music type. So this makes sense. We needed to know the class in order to derive from it. But then below that, we have classical.h. It's the exact same thing. It's going to also derive from music type. Here's where it gets tricky. At the bottom, we have playmusic.cpp, and that's going to include jazz.h and classical.h. Now, as soon as we do that, remember jazz.h included musictype.h, and so did classical. So we have two definitions of class music type, and that's not good. In C++, you can't have two definitions. So we have a problem, but there's a common solution to it. And that is, here I've described the problem. We have music type included twice. The solution is to use something called inclusion guards. So the first line here, we have pound if not defined music type _h. It's really common to use the file name, or if you might have duplicate file names, then you might have the entire path or namespaces or something like that. But you have some unique identifier for this file. So here we're using music type _h. And then remember, the first line is if it's not defined. So the second line is define it. And then we include all the normal code, and then we have pound and if. So that means the first time this file is included, it won't have been defined, and we define it, we include all our code. And then the second time this file is included, if not defined, well, it's been defined now. The first time defined it. And so we skip all of the code and we don't define it a second time. We don't have duplicate symbols, anything like that. So this is how we protect ourselves and allow including the same file multiple times. Okay, destructors and scope. So let's say I'm trying to represent a resource in Java. The resource might be a network connection or a database connection, or even something physical like a sound card or a GPU or something like that. When I want to release this resource, I might call .close. But this actually leaves room for mistakes. Maybe I'm going to forget to call .close. So what I could do is when I write my class, I could override the finalize function. For people who are not familiar, in garbage collected languages, there's often something like this where when the garbage collector comes and cleans up all this memory, it will call this function, and that's a way to automatically do the cleanup. And that's good, that's better, because now I can't forget on accident. But there's a problem with it. We don't know when the garbage collector is going to run. In fact, we don't know if it's going to run at all. It might never run. So this finalize override, that's not really a solution. It's a little better, I guess, but we haven't really gotten what we want yet. What we really want is, as soon as I'm done with it, automatically release the resource. In C#, the using keyword was added for this. And the idea would be, you say using my variable, some block of code, and then at the bottom of the code, when we exit that block, the garbage collector is invoked for that object, and it'll automatically clean it up right then and there. So now we do have control over when finalize gets called. Java 7 added something very similar called automatic resource management. But at the end of the day, we still have the exact same problem that we originally had. The problem originally was if I forget to call .close? Well, what if I forget to use the using keyword, right? It's the exact same thing. And so we still have this same desire. I wish I could automatically release the resource when I'm done with it. That is where C++ destructors are very powerful. Here we have a destructor example. We have a class, and then you can see there's a function, and the function name starts with a tilde, and then it's the class name. That is a destructor. As soon as this object leaves scope, this function will get called. You don't have to wait for any garbage collector or anything like that. So as an example, here we have this function doThing, and we create a destructor example. And then at that closing bracket, that is where the destructor gets called. And it gets even better. You can insert scopes wherever you want. So here we call doFirstPart, and then we insert a scope for our destructor example. At the bottom of that scope is where the destructor gets called, everything gets cleaned up, before we call doSecondPart. So this is really, really helpful for if you are trying to represent resources, like I mentioned, a network connection or a physical thing like GPU, something like that. Now that we have destructors, we have the ability to represent resources safely. And the next up is RAII. It is the other side of representing a resource. Destructors are called when the object is being destroyed. RAII is for when an object is being created. And this kind of allows us to encapsulate the entire concept of a resource. RAII stands for Resource Acquisition is Initialization. The concept is you cannot possibly create this object unless it is a valid object, a valid resource. So here is some old style C++. Don't do this. This is just to illustrate the problem that RAII solves. So here we have this resource GPU, and then we call .open and try to get access to the default GPU. And then we have to check if we actually got access or if it failed. So this has a few problems. One, I was able to create the object before I actually opened it. So at that point, the object doesn't actually represent a GPU yet. And the second thing that I really dislike is we have that .failed function. That means I have to check if there was a mistake. And if I call any other member functions inside those functions, it's probably going to check, hey, by the way, have we actually acquired a resource or are we still in this invalid state? So as is, this GPU class represents two things. It represents both a GPU and some invalid state. That's not what we want. That's what we're going to avoid with RAII. So here are two examples of ways you could do it better. If I know that I will always guaranteed successfully get a GPU resource, then I can just make a factory function that returns a GPU. No problem. Easy as butter. Everything's fine. Easy as butter. I meant smooth as butter. Anyway, not everything's going to go that smoothly. Guaranteed success is a rare situation. So the second is a more likely scenario. In Chromium, we have this base optional, but if you're writing standard C++, you have standard optional. And the maybe succeeds function will return that. So what this optional does is it's either the GPU that you actually wanted or it's nothing. Now what that does for us is it means the GPU class now gets to represent only a valid GPU. It doesn't have to represent that second state where like maybe it's invalid or we haven't allocated it yet, something like that. Now the responsibility for maintaining that second state belongs in this optional class. So now we get to have a GPU class that actually is exactly what it should be, and we have ways to destroy it and clean up the resource, and we have ways to create it and guarantee that it was created successfully and we don't have to check if it failed or anything like that. So next up is pass by value and pass by reference. If you're writing Java, this is what a function might look like to you. We have this void add to dictionary word new word. If I copied and pasted this exact same code into C++, we would call this pass by value. And old style C++, we would think when you call this function, it's going to make a copy of the word that you pass in. Within the function, that copy is ours to manipulate however we want. And then at the end of the function, that copy gets destroyed. By the way, before I go further, the concept of pass by value, if you think of an integer is a type, it's not a value. 1 and 10 and the name Chris, those are actual values. So there's this kind of movement right now to treat things more like values and pass things around as values. So the alternative to pass by value is pass by reference. So in that first line, it's the exact same function, except we put a little ampersand after the type. So this means the thing that's being passed into our function is no longer a word. Instead, it's a reference to a word. This is actually very similar to how Java works. Inside this function, we can alter the word, and any changes we make will be reflected outside the function. So we're actually altering the original object itself, not a copy of the object. This has some benefits. Maybe the class being passed in is really heavyweight and making a copy is very expensive. So to avoid a copy, what we can do is pass in a reference instead. There's something I want to point out though. Well, two things. One, references are cheap, but they're not free. If I have the object passed in, then it's going to be in memory close to where I'm accessing. But if I have a reference, then the thing that's close to me is the reference, and I have to go fetch the object that actually lives far away. So this memory reference, maybe it has to go fetch more memory and bring it to the CPU, and that might be a little bit of delay. So even though references are cheap, I don't want to give the impression that they're free. They're not. The second thing that I really want to point out is that garbage collected languages use the word reference to imply a memory safety. Maybe things are reference counted or something like that. That is not what C++ means when it says reference. In C++, reference only means I have a pointer and I can go fetch the object itself. It does not give you any safety. So be careful not to fall into that trap. So in that last slide, the reference allowed us to modify the existing object, and maybe we don't want that. So what we can do is make it a const reference. So now, not only is it not a word being passed in, nor is it a word reference being passed in, it's a constant reference to a word. That means that it's lightweight, I have a reference, but I can't alter the thing that's being referenced. So this gives you a little bit of protection, and you'll see this often. In old style C++, this was kind of the default. We didn't want to make all these extra copies, and so we would have all these const reference parameters. By the way, when I talk about old style C++, at the end of this presentation, I'll be talking about move semantics, and that's how we get into new style C++. And I'll talk about it a little bit here on this slide too. So here's those three examples that we just gave. I want to give a general guideline when to use each one. So the first one, the const reference, that's if you're only observing the value. And here, if we're adding a word to a dictionary, kind of makes sense that we're just observing it. We don't really need to modify the word. We don't need to take ownership or anything. We just need to see what the word is and add it to the dictionary. The second example is if I want to modify the actual thing. That's when you would use that. So for example, let's say I create an array, but I need to initialize the array. So I can pass it to this function and say, hey, here's my array, please initialize it for me. Then the third example, where we're passing the object by value, there's two times that you might want to do this. One is when it's really cheap to make a copy. So for example, integers are extremely cheap to copy. It'd be better to pass an integer by value than by reference. The other time you would do this is if you're possibly taking ownership of that object inside the function. Now this is where it gets into new style C++. The concept of ownership is that I currently own this object and I no longer want it. I want to pass ownership to this other thing. So for example, maybe I've initialized the array and now I'm going to pass ownership over to the maintaining function, and it's going to maintain it from now on. But I no longer want to deal with the array. That's the idea of passing ownership. And if you're passing ownership, you might pass by reference, or excuse me, pass by value. Okay, the standard library. So in C++, the standard library is very big. There's lots of functions available to you, lots of classes and containers and all that stuff. However, C++'s standard library is very small compared to most other languages. For example, in Java, we have java.net.uri or java.net.socket. We don't have anything like that in C++. So if you're a C++ programmer, it's really, really common to find a library that does the thing you need. Typically, other programmers already know what libraries are best, and you can kind of follow the herd mentality. And over time, we're adding more and more to the standard library, but it's going to take us a long time to get there. So just be aware that the standard library, it's big, but it's nowhere close to what you might be used to. There's 3 parts of the standard library that I really want people to become familiar with, and they're probably going to be very easy, but it's worth pointing them out. And those are strings, vectors, and smart pointers. So for string and vector, there's the files that you include, and they look exactly like you might expect. Standard string dog name equals Fido, or standard vector of integers, some integers equals 1, 2, 3, 4, 5. It's very typical. A vector, by the way, is an array that can dynamically resize, so it can grow and shrink as needed. You can also combine these. So at the bottom, we have a standard vector of standard strings. We could initialize those with multiple strings. I mentioned that there's smart pointers, and I have a whole section on that. I'll get there first, or I'll get there in a second. But first, I want to talk about something that we don't use very much in the standard library, and we should be using a lot more. Those are standard algorithms. So for example, we have standard sort and standard copy if. I think us programmers, maybe in school or something, we were asked to write a sort function. And so we just kind of built up this habit of writing the code ourselves instead of using the existing sort function. And I think that pours into other ideas like copy if. The way copy if works is you pass it a container like a vector and a destination container you want to populate. And you're going to copy values from the original container into a second container only if the value passes some predicate. So maybe the predicate is my value greater than 10? If it is, then copy it over. That's a perfect example of something that I think it'd be very easy for us to rewrite instead of using the standard algorithm. So what I want to impart onto all of you is don't forget the standard algorithms exist. They're good, they're very well written, very clean and optimized. And a little bonus is if you use them, chances are you will impress the fellow C++ programmers because we all forget to use them. And as soon as we see it, we go, oh, okay, neat. I forgot about that. So you'll win a few bonus points. Okay. Smart pointers. Before I go on, I have some questions here people have been asking. Somebody asks, why is it that sometimes for declarations of some class is preferred rather than include of some class.h? So the reason is if you include, what's going to happen is it has to go open that file and copy all of the contents. And maybe you don't actually need the entire definition of some class. So for example, let's say I have a function and my function takes a pointer to some class. The pointer is always going to be the same size in memory. It doesn't care what the class itself looks like. So in that case, I just need to know that some class is a class, and I can just forward declare it, class, some class, semicolon. Then I don't need to go open this file and copy all of its contents. So my function declaration can just say, here is a pointer to some class, whatever. However, when I go to implement that function, chances are I'm going to be dereferencing that pointer and getting access to the class itself. In that case, I'll probably need to actually include the file and see what the class looks like. The second question is, are there any resources or places you would recommend to learn more about RAII? Sorry, still trying to understand it. That is totally understandable, your situation. I've actually received feedback that my description of RAII isn't very clear, and I'm trying to improve that. I don't have a specific example to point you to. I think that in general, if you just search for RAII, you'll probably be able to look at a few links and say, this one's too complicated. This one, I don't know what they're talking about. Here's one that makes sense. So unfortunately, I'll probably have to keep the burden on you. You might have to find it for yourself. But I do want to tell you, after this presentation, there is a hallway that we can all meet in and talk there. So I can try to do a better job describing how our AI works in the hallway afterwards. So perhaps meet me there. Okay, a new question. What are the differences between int array 10 and vector int array 10? When to use one over the other? So the first one is an actual array. The second one is a vector. In an array, objects will be right next to each other in memory, and you have to keep track of the size of the array separately. You have to remember this thing is only 10 items long. A vector is different. A vector can expand and shrink, and you can ask it how big is the container right now. So if you want it to be able to grow and shrink, use vector. Vector is also just a really safe default. Even if we're using an array, the ability to pass it around and know the size and all that is just really nice. So a lot of C++ programmers have kind of fallen out of love with actual arrays and started to default to vector. And vector is a great default. You can almost default to it all the time, and most of the time you'll be fine. You can just make exceptions as you go. One more thing I want to point out, vector is a standard container, and as of C++ 11, there's now a standard array container. It's kind of like vector. It doesn't resize, but it does know its actual size, and you can pass it around and people like it just like they enjoy vector. So, you might consider that as well. Next question. Are there API references for Chromium-specific base functions classes, aside from searching through the header files? So what you can do is go to cs.chromium.org. That's code search. And you can type in base and see all the various base things there. As far as API references, Chromium is very nebulous. It's shifting and changing all the time. Base things are less likely to change. Those are pretty stable. But because in general Chromium is shifting and changing, we don't have a whole lot of API references. We don't have a lot of documentation. But if you go look at the base, for example, base optional, if you look at that file, those are very well documented. There's all sorts of comments in the file explaining what the class does, how it works, what each function does. So that's probably the place to look. Okay, so I think that caught us up with all of the questions. Yeah, we will go back to smart pointers. So you've probably heard about pointers in C++ and heard maybe horror stories. The first time I gave this presentation, I said, everybody in the room, raise your hand if you've had some nightmare about C++ pointers. And the entire room raised their hand. It was crazy. It was like even the people operating the soundboard and video camera, all of them raised their hand. It felt like it was bonkers. So what I want to point out is smart pointers are different. Raw pointers can be dangerous, but smart pointers are pretty darn safe. That's not 100% true. You can still get into problems, but it covers a lot of the easy mistakes for you. So if you come from a garbage collected language, you're probably familiar with the idea of references, and if anything has a reference to this object, then the object is alive. And there can be multiple things with a reference to that object. In C++, that would be a shared pointer. And the way it works is just a reference counter. So as more objects get references to this object, the reference count goes up. And then once the reference count goes down, because the references have been released, when it hits 0, the object gets cleaned up. So this gives you a sort of garbage collected type behavior. But there's something I really want to point out here. Multiple ownership is weird. I know that in garbage collected languages, that's the default, and so that's just what you do, and you don't even think about it. But in reality and in C++, it's not like I own my house and my friend owns my house and my dog owns my house. It's not like that at all. It's really strange to have multiple ownership. So when you're programming, you probably don't want to just default to using shared pointer, even though it's kind of an easy thing to jump to. What you want to do is have a very clearly defined, my object is created here and it's destroyed here. And between there, it will be owned by this other object. That's what you really want. So the way to represent that, here's a slide saying exactly what I just mentioned, that you don't always want to use shared ownership. So the way you'd represent unique ownership is with a unique pointer. So only one reference can own the unique pointer. As a result, you can't actually copy a unique pointer around. You have to move it. I'll get to that in just a second. But this is a more safe default. This is probably what you should be going for instead of shared pointer. If you do genuinely have a multiple ownership situation, then fine, use shared pointer. It's the right tool for the right job. Just, don't default to that. Perhaps default to unique pointer. So here I mentioned we can't copy unique pointer. We have to move it. The way that works is, earlier I mentioned, I've initialized this array. I'm done initializing it. I'm going to pass ownership over to this other thing, and that other thing will maintain it. That is where standard move comes in, when I'm transferring ownership. So that makes sense. If it's a unique pointer, maybe right now I own the pointer, but I'm transferring ownership elsewhere, so I'm going to move ownership. And finally, we're going to get into move semantics. This is new as of C++ 11, and it kind of undoes a lot of our old habits. If you've been programming in C++ for a while, you've developed code smells, and you'll see something and be like, oh, that's going to make extra copies. That's not good. Move semantics changed all that. We need to unlearn our old habits and learn some new habits. If you're just now coming to C++, then that's good. You don't have to unlearn anything. You have an advantage there. So here is just some really simple code. We have a function getName. It returns a string, and it initializes just a temporary string, fills in the name Chris. And then at the bottom, we have presenter.setName, and we give it the result of the getName function. So you can imagine we have this temporary. It has a buffer, and it filled the buffer with the values spelling out Chris. And then the presenter is going to have its own string, and that string is going to have its own buffer, and it's going to copy, I need room for 5 characters, so allocate enough in my buffer, and then copy each character one at a time, and now we have our name in presenter. This is interesting because we have 2 buffers with the same values, and the one is a temporary. We know the temporary is about to be destroyed. So we can be a little tricky here. What we could do is say, I'm going to steal the buffer that the temporary has. Now I don't need to allocate my own buffer, and I don't need to copy the values over. They're already there. I just stole the buffer and everything's fine and dandy. And then the temporary buffer, I'm going to set it to null so that when it gets cleaned up, it doesn't have to delete any memory. It doesn't have to do anything with its buffer. It's all taken care of. So that way, we saved a lot of work. We didn't have to do any of this fancy buffer management. That is all move semantics is. Move semantics is just the ability to know that something is about to be destroyed or you're transferring ownership, and it's safe to steal the buffers from it. So here is 2 functions you might see inside a class. The first one is a copy constructor, and the second one is the copy assignment operator. Those both take a const reference, and the idea is, you pass in a thing, I'm going to allocate my own buffer and copy from your buffer. As of C++ 11, there's now a move constructor and a move assignment operator. And the way these work, you can see instead of a single ampersand, it's a double ampersand. That is an R value reference. And the R value reference just means it's an object that's about to be destroyed, and it's safe to steal the buffer from it. And you'll also notice it's not const. So that is, we want to set its pointer to null, so I need to be able to modify it, so it can't be const. That's all there is to it. So here is that original thing. We have string name equals Chris, and we have presenter.setName, and I want to pass in that name, but I want to pass it in a way that it can be moved. So what I could do is cast my string to an R value reference of a string. That's what that static cast to a string R value reference, that's what that's all about. That's saying that it is safe to steal the buffer from this string. And after I do that, I don't want to touch this object at all. It's now kind of dangerous. I don't know what state it's going to be in. Just a thing to be aware of. Once you move from an object, probably best not to touch that object. And you'll notice that cast is really messy. It's kind of hard to read. That is all what standard move does. It is simply a cast to an R value reference of that type. So an interesting thing to point out, standard move doesn't actually move anything. It does nothing. It simply casts it to something else. But in the act of casting it, once we pass the casted object to a function, that function now has the ability to steal buffers. So move is really more of an indicator that it's safe to move this thing. So here we have class talkPresenter, and we have two set name functions. The first one is the copy version, and the second one is the move version. Now this runs into an interesting problem. Let's say somebody reports a bug, and I go into the copy version of the function and I fix the bug, and I forget to check the move version. If that happens, I now have the bug and I missed the whole reporting and all that. I've got a pretty big issue. And this is only if I have one parameter that can be either copied or moved. What if I have two parameters? Well, now I need four functions. I need an L value, an R value, LL, RR, RL. So you get this geometric explosion with more parameters means more overloads of this function. Now that's not good. And this actually created a stir in the C++ community. We started saying, we don't even know how to write functions anymore. This is a complete mess. What have we done? But we have a solution. It's not perfect, but it's a trade-off, and it's a well-informed trade-off. So what we could do is just have one function, and it takes the parameter by value. So this is interesting. If I call presenter.setName, and I use my old style C++, my old code smells, the old habits I need to unlearn, I will be thinking, oh, this is going to make a copy, and copies are expensive, and that's a bad habit. Don't write this function. But in new style C++, that's not really true. So let me explain what's going to happen. Remember I said pass by value is going to create a new object. If I pass in a name, a string, it will create a new string, and I can make modifications. I can do whatever I want to that string. I'm only modifying the new one. So when we create that new string, there's two ways we can create it. We can either copy construct it or move construct it. So if somebody calls our function and moves in a string, it'll call the move constructor, and now we're just continuing this train and moving further and further down. That's really cheap, and that's fine. Or the object can be constructed with a copy constructor. Now, if I'm going to be storing the name inside my class, then I might copy it from the parameter into my member. But because I've already made a copy, what I can do is move inside this set name function. I can say, my name equals standard move name. And if I do that, now I haven't introduced any extra copies. I was already going to have at least one copy. All I've introduced is one extra move, and moves are cheap. So the benefit here is now we don't have a geometric explosion. We only have one function, and that's good. The downside is we have one extra move, but moves are supposed to be cheap, so it's a trade-off. It's completely worth it. Nobody's going to care about the cost of a move. Okay. And here's an example of how you can pass it down further if you want. Process name is standard move name. So that's everything. Thank you everybody for joining. here is an email address. You can send me questions if you have any. There's also, you can reach out on social media. And I'm going to be joining the hallway. You can ask me questions there. And lastly, here's slides and a video of the original presentation and differences between 1.0 and 2.0. And that's all. Thank you, everybody, for joining.